Hey there! Once again, it's Raiaan from Roots of Unity, and today we'll be looking at the last video from our trigonometry series. In this video, we'll cover identities. We'll look over the compound angle formulae, double angle formulae, and so on. So let's get started. Firstly, we'll go over the compound angle formula. There's many ways to prove this. I'll show you what I thought was the easiest. Don't get scared by this diagram, I'll walk you through step by step. Let us establish what exactly we're looking for here. So taking this angle as x and this one as y, we're trying to find the expression for sine x plus y. Obviously, that is going to be opposite by adjacent, which is BE by BA. In this case, BA equals to 1, so it just equals to BE. If you look at the diagram, BE equals to BF plus FE, which in turn equals to BF plus CD. Now, our goal is to find these two lengths in trigonometric terms. Let us state some properties of this diagram. These two are vertically opposite triangles, so these two angles both equal to y. We have sin x are equal to oppo by hypo, or in this case BC. And similarly, cos x equals to CA. Looking at cos y, we see that it equates to BF by BC, which in turn can be written as BF by sin x. Then we can rearrange to find BF, which is cos y sin x. Using a similar method with sin y, we can find CD, which equates to sin y cos x. Hence, we can deduce that sin x plus y equates to cos y sin x plus sin y cos x. You can pause the video to take a closer look. Now, let's find some more related formulas. Let x be d minus x and y be minus y. Substituting in the original formula we found, we can make use of the symmetry properties and rearrange to find the equivalent of cos x plus y. Similarly, if we take y as negative y, we can find sin x minus y. I let the rest of the related formula be exercises for you to try out. The general process should hopefully be clear by now. Next up, we'll look at the Dowel angle formula. This is closely related to the compound angle formula. Just let x equal to y. Thus, sin x plus y becomes sin 2x and so on. The cos 2x formula is very important as it can be rearranged multiple ways. With the help of the identity sin squared x plus cos squared x equals to 1. So, we are basically simplifying the compound angle formula as necessary. Take another look at the formula so far before we move on. Next, we'll take a look at some other formulae. Starting off, we let r sin theta plus alpha equal to x sin theta and y cos theta. We know already that sin x plus y equals to sin x plus cos y plus cos x sin y. We rewrite that in terms of theta and plug back into the main equation while multiplying with r. Next, we equate the coefficients. After cancelling them out, we're left with x equals to r cos alpha and y equals to r sin alpha. So, let's take x squared plus y squared. Instead r cos alpha and r sin alpha, we expand and substitute cos squared alpha and sin squared alpha with 1. Hence, r equals to square root of x squared plus y squared. Similarly, let's divide y by x. That gives us r sin alpha by r cos alpha, which is basically tan alpha. We rearrange to see that alpha equals to tan inverse y by x. So, these are the identities we have established so far. Using compound angle formula, you can easily figure out the rest of these. Given that r is equal to x squared plus y squared and tan alpha equals to y by x given alpha is within 0 to 90 degrees. Now, it's time to start the problem solving segment. Can you solve for cos 75 without using a calculator? Using the formula we just learned, we can break down 75 into 30 and 45. We know the values for cos 30, cos 45, sin 30 and sin 45. Plugging them into the equation, we get the answer as 0.258. Next, given that sin A equals to 4 by 5 and cos B equals to 5 by 13, that A is obtuse and B is acute, we have to find tan A minus B. Firstly, we decide what quadrant the points lie on. Since A is an obtuse sine angle, it falls under the second quadrant. Making use of the Pythagoras theorem, we figure out the adjacent side, which is 3 units. Hence, we can find tan A easily. Using a similar approach, we find tan B. Here, cos is acute, so it falls under the first quadrant. Then afterwards, we pull up the tan a minus b formula, inserting all the values we just found. There's your answer. Now, we'll try and prove the following identity, which may come up quite often in questions. We have to prove that sine 3x is the same as 3 sine x minus 4 sine cubed x. Taking the left hand side, we break it down to sine 2x plus x. Then we expand and substitute again, making use of the variance formula. Our aim is to bring everyone down to in terms of sine x. Here it is. Now this one's pretty lengthy. Let's focus on one part at a time. We try to prove that cos 60 minus x plus cos 300 minus x equals to cos x. We already know the values of cos 60 and sin 60. Cos 300 and sin 300 can be found using the symmetry properties. Plugging them into the equation lets us cross off two values and hence end up with cos x. The second part asks you to find the exact value of cos 15 plus cos 255. This is a one-liner. It's obvious that the extra equates to 45. Hence cos 45, which gives root 2 by 2, is our answer. In the last part, they ask you to solve the given equation for 0 to 180. We know already that the first part just equals to cos x. Rearranging gives up 4 cos x sin x, which can be broken down to 2 into 2 cos x sin x. Inserting the relevant identity and using limits properly, we can solve the equation here. Lastly, we'll take a look at yet another multi-phase problem. Firstly, we're supposed to prove the following expression. Once again, we start off with the basic idea of using identities and substitution. Generally, rearranging the components helps with these equations, and you might need to convert every second to a sine value and so on. Anyways, I use C and S here to represent cos theta and sin theta in order to save time. Next up, we express 4 cos theta minus 6 sin theta in the r cos theta minus alpha form. For this, we need to find r and alpha as follows. Then just write down the expression. Lastly, we find the greatest value of this. We input the RHS form from the first part of the equation and then convert it to the format in the second part. The greatest value happens when the cos squared alpha segment equals to 1, hence at 52. And that wraps up our series on trigonometry. I hope this series helped you gain insight into how trigonometry works. Thank you for sticking by.